Swayam Prabha. Digital India. Educated India.
Okay. So again, one more definition before we can prove a result. So this is what is called as a sunflower. Okay. So a sunflower is a, so this is basically nothing to do with graphs. This is actually a result from just set theory, and okay, I will come to the result later. So our sunflower is a collection of sets Z1 up to Zp such that for all I not equal to j, Zi intersection Zj is the same. Okay. And this common intersection is called the center of the sunflower. Okay. So this is actually that, I mean, if you just draw this, it will be kind of apparent why it's called a sunflower. So let's say this is my one set Z1, then I have something else as Z2. Okay. So they can have some common intersection. Now what it is saying is that for every other set, the intersection of Z1 and Z2 with this other set is exactly the same as this. Okay. So Z3 is something like this, maybe I have a Z4 which is again exactly this, and so on. Okay. And this region is called as the center. Huh? Huh. So now we will prove a result which was due to Addition Rado, yeah. So this was in 1960, I think 60 or 62, who showed, and this is popularly called as the sunflower lemma. Yeah. Let's say sunflower theorem. This was due to Erdős and Rado. So they showed that let Z be a collection of sets such that each set has size at most L. Okay. Then if the size of Z is greater than so we need number of sets also, so Z be a, okay. P minus 1 raised to the power L times L factorial, then Z has a sunflower with P, okay, so I haven't defined this, P petals. Okay, so petals are essentially these sets. Okay, so these also called petals. Okay. So basically what it is saying is that if I have a collection of sets which are not too large, which is bounded by L, and if Z is large enough, then it will have some sunflower consisting of P petals. Okay. So how do we prove this? So we'll prove this by induction on L. Induction on L, right? Yeah. So what happens if L is equal to 1? So suppose each of the sets have size at most 1, then what happens? Yeah, so if exactly, so basically if the sets have size at most 1, then they don't have any common intersection. Okay, so therefore Z greater than this quantity implies that, so L is 1, so P is at least 2, so this means that Z is at least 1. Okay, so basically huh?
It is strictly greater than P minus 1, so Z is at least P sets, and though we can take those.
Okay, so Z is at least P set, so Z is at least 2, yeah. So then basically the what? They can be any elements, there is no restriction on that. So that's what I said, this is just a result in set theory, this has nothing to do with graphs or anything, they can be any elements. Okay. So essentially what you do is that in this case the sunflower is basically all the sets of Z. Okay. So the sunflower is all sets in Z, and by this thing there are at least 2 sets. So therefore the sunflower has 2 petals. That's what we require. Well, this quantity is actually bigger than greater than or equal to P, that is why we have P petals. So now let's look at the case when L is greater than or equal to 2. Okay. So if L is greater than or equal to 2, what we will do is, so first we will consider a maximal subcollection of Z which is disjoint. So let M be a maximal subcollection of disjoint sets in Z. Okay. So, and let S be the union over all these sets. Okay. So, union over all, let me call them as maybe A belonging to M of A. So, what can we say about the size of S? So, each of these, so each set in Z has size at most L. Okay. Now, okay, so before getting into that, I had to say one more thing. So, if . size of M is greater than or equal to P, then by that same logic as above, M forms a sunflower, okay, and we are done. So, basically by the same logic as above, if let us say the size of M is at least P, then it forms a sunflower which has P petals, and of course, the center is empty, there is no, they are all disjoint, but that is okay. So, we already get a sunflower. Now, suppose M is less than P. So, if M is less than or equal to P minus 1, what can we say about the size of S? So, there are this many, so if M is this much, so there are this many sets in M, okay. S is basically the union of all these sets. By definition, they are all disjoint. Each set has size at most L. So, this will be of size P minus 1 times L, right. This is a trivial upper bound. Now, note that S intersects with every set in Z. Why is that true? So, first of all, it intersects with every set in M, because it is the union of all the sets in M. So, clearly it has intersection. Now, the other sets in Z which are not in M, why does S intersect with those sets? Because by choice, right, because it is chosen to be maximal. Okay. If S did not intersect with some other set in Z, then that would have also belonged to M. Okay. By choice of M. Okay. Therefore, there exists an I in S such that I belongs to at least P minus 1 raised to L minus 1 into L minus 1 factorial sets in Z. Okay. So, Z has a total of at least these many sets. Okay. The size of S is bounded by this. Okay. So, therefore, suppose if this were not true, okay, so suppose if let us say every I in S intersects with less than these many number of sets, then this times the number of elements in S, okay, is kind of a an upper bound on the number of elements in Z, which will be less than P minus 1 L into L factorial, okay, just multiplying these two. But we know that Z is greater than this, therefore, that cannot happen. This is just simple counting. So, now what do we do? So, we have this many sets in Z which are which contain I. Yeah, so it will be strict because that is strict inequality. Yeah, so this is actually a strict inequality because Z is strictly greater than this. Yeah. So now we define the collection Z prime to be all sets of the form x minus I such that x belongs to z and I belong to x. Okay. So, look at all the set x in z which contain I and remove I from that set. So, this is basically z prime, right. How many, what is the size of z prime? So, we know that by this claim above that z prime has size greater than p minus 1, L minus 1, L minus 1 factorial. And now note that this satisfies the hypothesis for induction hypothesis for L minus 1, okay, our statement. So, therefore, by induction Z prime has a sunflower with p petals, right. So, this is, we have L minus 1 here. Okay. So, therefore, by induction hypothesis Z prime has a sunflower with p petals. Now, how do we get a sunflower in Z with p petals? Exactly. So, in all these sets that we have, just put back I, okay, and it still remains a sunflower. It's just the center of that sunflower increases by one element. So, get a sunflower for Z by adding I to these sets. Okay. That completes the proof.